The bad news is that half the people in this room will at some point experience chemotherapy. And that is because for people like us, living in a country like the UK and the US, our lifetime risk of developing cancer is 1 in 2. And almost every cancer diagnosis will be followed with a treatment plan, and almost every treatment plan will involve chemotherapy. I'm one of these unlucky people in the room who has experienced cancer. In 2006, I was diagnosed with acute lymphoblastic leukemia, and as a result, I underwent induction and ablative chemotherapy before receiving a stem cell transplant. And as most of you know, cancer therapy is difficult. I can verify that from personal experience. And it's not simply difficult physically, but it's also very difficult mentally and spiritually. I have distinct memories of waking up in the morning and simply dreading the day that is to come, because I knew that I had to get out of bed, get dressed, get in the car, get to hospital, and then I had to submit myself to another round of chemotherapy that will make me even sicker and even weaker. And during those days, all I wanted to do was to hide, to run away, so that I can recover just a little of my energy or my vitality of the person that I used to be. But this wasn't an option. It wasn't an option if I wanted to see out another Christmas. So I put myself through it. And it's not an experience I would wish on anyone, and certainly not half of you here today. Thankfully, making chemotherapy more effective and more tolerable is an active area of research. A lot of the work has been involved in the development of new drugs or new vehicles to deliver these drugs that are more effective, that have fewer side effects, and that are more tolerable. But I think that won't be enough, because the fundamental problem of drug delivery, the problem of how do we get these drugs to the cancer cells, has not been solved. And to illustrate what I mean by the problem of drug delivery, here is an image, a microscope image, of the inside of a mouse tumor. In red are the blood vessels. These supply nutrients and the drug. In purple or blue, depending on your color preference, is the drug doxorubicin. And in green are hypoxic cancer cells. These cancer cells have a special metabolism that enables them to survive longer. And because we're looking at the inside of the tumor, everywhere else on this image that is black are filled with cancer cells. And you can't see them because this is a fluorescent image. And this image demonstrates very nicely the problem of drug delivery. Most of the doxorubicin, the drug that we're using to treat this cancer, is only found around the blood vessels. Very little of it can be found amongst the green hypoxic cells. And we have these large areas, these voids of darkness, where there are cancer cells, but there are no drugs. And what that means is that even if we replace doxorubicin with this amazing, all-powerful drug, the overall treatment is still ineffective. And if we can solve this problem of drug delivery, if we can make this image entirely blue, then we can significantly increase the efficacy of chemotherapy. We can reduce the dosage we use in patients. We can reduce the number of treatments they need. And all of this will go a long way to reducing the burden of chemotherapy. And this is the problem I'm here to solve. And I'm here to solve it using ultrasound and microbubbles. And the way it works is that we would administer the drug as we currently do, but at the same time, we administer a population of microbubbles as well. And when I say microbubbles, these are air bubbles that are encapsulated within a bilipid layer, and they have size of around 10 microns or less. At the same time, we position an ultrasound transducer over the tumor site. And when the drug and the bubbles travel to the tumor and they encounter the ultrasound, the interactions between the bubbles and the ultrasound will serve to disperse the drug throughout the entire tumor, not just around the blood vessels as we've seen previously. And by doing this, we can significantly improve drug delivery to tumors. And to demonstrate that this actually works, Here is a mice study of this technique. What you see on screen are 5 separate experiments on 5 different mice. The tumor on the left, within the solid circle, has been treated with a drug, plus ultrasound and microbubbles. The tumor on the right, within the dashed circle, has only been treated with the drug. And the scale bar represents the degree of drug uptake. That is the number of cells that has been exposed to the drug and absorbed it. And you can see immediately that ultrasound and microbubble has caused a significant increase in drug uptake in the tumor within the solid circle and in the left in general. And if you crunch the numbers, the enhancement is 5 times. That is, ultrasound and microbubbles resulted in 5 times as many cells being treated in the tumor than without. Now imagine if you can translate this into patients, making chemotherapy 5 times more effective. Instead of over a month in hospital, you spend a week instead. And not only would you reduce the time in hospital, you will also increase your success rate as well. And now imagine instead of 5 times, we can do it 10 times, 20 times, 100 times. And this is what I want to do. I want to achieve these images for patients so that you go in for chemotherapy and you come out and it's done. But this is done in mice. And mice are very different to people. And in order to properly do this in patients, we must first understand how this happens. And to do that, we must understand the mechanisms, the interactions between ultrasound and microbubbles that produce these images. And that is the focus of my research. And to demonstrate what I mean by ultrasound and microbubbles, because after all, how can ultrasound and microbubbles do this thing, this amazing thing that we've seen? And I'll show you 2 ways that ultrasound and microbubbles interact that we think is responsible for this enhancement. The first is an interaction called microstreaming. This is where a bubble oscillates in response to ultrasound, and as it does so, it pumps the fluid around it in these circuitry flows. And this is what it looks like under a microscope. This is a relatively fast process. And if this happens near a boundary, such as a blood vessel wall or cell membrane, the shear forces generated by the flow flowing past the boundary is enough to tear the boundary open slightly to allow easier passage for drugs. Additionally, the vortexing action that you see, we think is also responsible for increasing the mixing between drugs and the cells and enhancing drug transport by convection as well. The next mechanism is called microjetting. This is where, due to the pressure of ultrasound, a bubble collapses, but it does so in such a way that it generates a jet of material. And this is a very fast process. The slide on the left is the bubble at its maximum size, and the slide on the right is the first frame in which the jet can be seen. And this entire process happens in 1 2 millionth of a second. It's very, very fast. And what that means is that this jet is actually moving at really high velocities. Modeling shows that this jet is more than capable on its own of punching through blood vessels and creating tunnels in tissue. And we think that it plays a role in enhancing drug delivery in much the same way that a truck driving down the highway would drag leaves behind it. That when this jet is formed, it's dragging molecules behind it, leading them deeper into the tissue than they currently go by diffusion or convection alone. And it is by studying these interactions and others like it, and how they operate in tissue to result increased drug delivery, that we'll be able to bring the benefits that we have seen in mice to patients. And so far, my research into understanding these interactions has revolved around the building of an instrument, a confocal laser scanning microscope. The microscope itself does not use a revolutionary technique, but it is unique in that it is an instrument designed to study these kind of interactions in real time during ultrasound exposure. This instrument produces images similar to this. This image is showing how the distribution of a fluorescent dye has been pushed towards your left by ultrasound. This is a test run just to make sure that everything works. This instrument is close to completion, and when it is completed, I'll be starting experiments in earnest in a variety of models, starting with relatively simple models that you can make in 2 hours, to more complex artificial tumors that you take weeks to grow, and ultimately in human trials. And the reason I'm taking this approach instead of jumping straight to mice models is because this will let me iterate very quickly for my experiments, because experiments like these and techniques like these have a lot of pitfalls that are not obvious until you do it. And if you start in mice models, not only are you dealing with all the experimental unknowns, you're also dealing with a very complicated organism at the same time. And let me tell you, no two mice is the same. The research I'm doing is part of a larger effort based in the Bubble Lab within the University of Oxford. And I'm very fortunate to receive funding and technical support from these other bodies. I would like to finish my talk the way I started. Half the people in this room will at some point experience chemotherapy. And it is my sincere hope that through my efforts and the efforts of others, that you will have an easier time of it than I did. Thank you.